Thank you for the very warm introduction, as well as for the invitation to talk here. And thanks to everybody for coming to listen. So since this talk is about thermodynamics, we should probably review briefly what thermodynamics is. Probably everyone here knows, but I have found that when I've asked physicists, they've tended to be unable to define thermodynamics for me, including physicists who say that they specialize in thermodynamic phenomena. Philosophers are probably better than physicists, but let's just ensure we're on the same page. Thermodynamics is the study of energy, the different forms that energy can be in, and the transformations amongst those forms. Thermodynamics was developed as a result of the Industrial Revolution. For the first time, steam engines were powering factories. Naturally, people wanted to understand how efficiently these engines could operate. These technologically motivated questions led to fundamental questions, such as why does time appear to flow in just one direction? And to also a brand of literature called the steampunk genre that is closely tied into some of those fundamental questions. But I'm going to assume during this talk that to most people, time does appear to flow in one direction. Why is that the case? Well, an answer that is commonly given in physics is based on the second law of thermodynamics. Perhaps the most famous formulation of the second law is every closed isolated system's entropy can only increase or remain constant. This is a simple early formulation of the second law. It comes along with some caveats that are a little less famous than the formulation as a whole that I'll talk about in a little bit more detail later. But to start with, the second law was constructed to describe large classical systems such as steam engines. And the steam engine was the transformative technology of the era. But today's transformative technologies include some very, very, very different systems, namely small and quantum systems. Hence the need for the field of quantum thermodynamics, which is my home base. In quantum thermodynamics, we go back to the laws of thermodynamics from the 1800s and extend them to show explicitly how they apply even to, say, systems that entangle with each other. We also do other things in quantum thermodynamics. We have other goals, but this is the one most relevant to this talk. Nowadays, many of us in quantum thermodynamics use the toolkits, mathematical, conceptual, and experimental toolkits of quantum information theory. And one way in which I think quantum information theory can be cast is as the understanding of quantum systems through how they store and process information. If you're interested in learning more about the field of quantum thermodynamics, then I can suggest these two reviews, which overview the kind of modern, recent formulation of quantum thermodynamics that has boomed over the past decade. The field has been moving very quickly, and these papers were originally written in 2015. So a lot has happened since then, but they provide really great foundations. Also, I wrote a book for the general public, including people in academia, about the field of quantum thermodynamics, the basic concepts, the background we need to understand it, the history, main ideas in different subfields. And it's written not in the style of a scientific paper, but a conversation that we would have over lunch if we happened not to have any napkins to write down equations on. So surely this field of quantum thermodynamics that has boomed over the past decade and been informed by quantum information theory, which developed, which kind of matured in the early 2000s, surely that's provided some new insights about the second law. Some of those new insights will be the subject of this talk. So in case you fall asleep in the next hour, here are the main takeaways. From quantum theory, we can derive more general and more refined variations on the second law. It had been hoped that we could use quantum phenomena to break the second law of thermodynamics. I don't know of a way to do that, although of course there is still discussion. And when I mean break the second law, I mean sensible modern formulations of the second law. And I'll discuss what I mean by those as well. However, we can use quantum resources to bend around the second law, so appear to violate the second law while in fact subtly getting around some of the assumptions behind it. And for this reason, we can use thermodynamics to understand better where the difference is between classical physics and quantum physics. So we often think about quantum theory as modernizing thermodynamics, but we can move in the opposite direction as well. Let's start with a little bit of basic background about the conventional second law of thermodynamics. The second law has many formulations. I won't bother reviewing most of them because most of them aren't directly relevant to the new research I want to present here. Perhaps the most famous formulation is based on entropy. There are even multiple versions of this formulation of the second law. I'm going to present one that I find intuitive following Boltzmann. If you don't find this presentation of the second law intuitive, that's fine. The results that I'm going to present do not actually depend on this particular formulation of the second law. I just want to present a little bit of background, a little bit of review to get us all recalling what the second law feels like. To introduce this formulation of the second law, we have to review entropy. It's useful to keep in mind our favorite thermodynamic system, a classical gas in a box. The system can be in some macro state that is specified by large-scale properties of the system, such as the total volume, the temperature, and so on. The system will also be in some microstates, specified by a list of all the particles' positions, their momenta, and perhaps other properties, depending on what sorts of particles we have. The system is in equilibrium if large-scale properties remain approximately constant in time, and there's no net flow of anything such as energy or particles into or out of the system. If we know that the system is in one macrostate, we probably won't know which microstate the system is in, because each macrostate is consistent with many microstates. And let's denote by omega the number of microstates consistent with a macrostate. Suppose that we know what macrostate the system is in. I am going to start talking about information and knowledge, and if that way of speaking doesn't appeal to you, again, that's fine. This is just basic background information to remind us what the second law is kind of like. The actual results do not depend on this formulation. We tend to assume that all of the possible microstates are equally probable. I'm not going to justify this assumption because it would require a whole other seminar. So each possible microstate J has a probability Pj that's 1 over the total number of microstates. Suppose that we find out which microstate the system is in. How surprised are we, or how much information do we learn? The amount is given by the surprisal, the negative of the log of the earlier probability of that microstate. By the way, I'm going to use base E logarithms because those are natural and useful in thermodynamics. That this formula makes sense Z to C to C in a simple limit. Suppose that the microstate is predetermined. We know in advance that only one microstate is possible. All of the other microstates correspond to probabilities of 0. We can plug this probability into this log. The negative of the log of 0, the negative of the log of 1 is 0. So supposedly we learn 0 units of information. Indeed, if the microstate was predetermined, then when we're told what the microstate is, we don't learn any information. So this formula, at least in a simple limit, checks out. And we can go into a lot more of the details about surprisal and entropic quantities and why they have the forms they have. A discussion of that is in chapter 1 of this book. We're not very interested in any one particular microstate, but suppose that we tell the same story about a number of trials and we average over many trials. So what is, on average, over microstates, the amount of information that we learn? Well, we're averaging this surprisal. We average with this probability weights, and this J indexes the possible microstates. For each piece of J, we can substitute in our formula for the probability. The sum n comes to be independent of the microstate J. So we can simply multiply the summand by the number of terms. So we have the number of terms times the probability, and those two factors cancel. Then by using a log law, we find the average surprisal is the log of the number of possible microstates. And that quantity is an information theoretic entropy. But thermodynamics, we said, is the study of energy. So it makes sense to come up with some quantity that has dimensions of energy. One way of doing that is to stick a factor in front of the log that has dimensions of energy. And a very convenient such factor in thermodynamics is Boltzmann's constant, a universal constant of nature, 1.38 times 10 to the negative 23rd joules. At this point, I am contractually obliged to show a photo of Boltzmann's honorary grave in Vienna, which is usually shown at this point in talks and textbooks. Although probably people don't usually tell you that Boltzmann was not actually buried here when he passed away. Physicists got together and petitioned the government of Vienna to give him such an honor until the government gave in and created this honorary grave for him. However, members of his family who passed away later were buried here. And we can see the Boltzmann entropy formula on the gravestone. Right, we've covered entropy. Now we need to move back to the second law of thermodynamics. Suppose that our favorite thermodynamic system is in some equilibrium macrostates. And this macrostate can be equilibrium with respect to some real or imagined internal constraints. For instance, suppose that the particles of this gas are clumped together in a corner of the box. This can be an equilibrium state relative to internal constraints that would harness the particles in place. We can have in mind some other possible equilibrium macrostates, and we can ask, under what condition can the first macrostate transform into the second spontaneously? The answer is governed by second law. The transformation can happen spontaneously if and only if the entropy grows monotonically. Moreover, seeing that the gas is expanding is what gives us the impression that time flows. This very widely used formulation of the second law comes with caveats. Again, both macrostates are equilibrium macrostates, and again, the gas is classical. These caveats ensure that the entropy is well-defined and unambiguously. Also, the system that we're talking about is very, very large if it is to strictly obey the second law as formulated there. Thermodynamicists like to talk about the thermodynamic limits in which the total number of particles and the volume diverge while their ratio remains constant. If the system is finite, then probably the initial macrostate will recur because the system effectively samples randomly from the space of all possible configurations, and that space is finite. Just, you'll probably have to wait a very, very long time before you observe a recurrence. The larger the system is, the more configurations are available to it, so the longer that you have to wait, and the longer you can have confidence in that formulation of the second law. We inherited these caveats from the 1800s. Extensions of the second law were proposed by the early 1900s already. During the 1800s, a lot of thermodynamicists didn't like the notion of atomism because thermodynamics was a very good theory, pretty accurate, and it just depended on large scale properties of systems. So why would anyone want to posit or deal with the notion of tiny particles that nobody can sense directly? But Brownian motion shoved itself onto the scientific consciousness. And so during the 1900s, the theory of atomism became more and more to be accepted. People came to accept that materials consist of tiny particles that move randomly, and so sometimes will move opposite the direction that we expect. But at least on average, the second law came to incorporate an average in some formulations. So some extensions were made even by the 1900s, but I'm going to talk about three newer extensions developed within quantum thermodynamics and non-equilibrium statistical mechanics. I'll start with second laws derived from resource theories for thermodynamics. I need to define the term resource theories, which is technical jargon I don't expect people here to know necessarily. Well, actually, philosophical crowd might be plugged into the resource theory literature. But first, before going into definitions, I'll preview the takeaway. That is, using these second laws from thermodynamic resource theories, we can answer a question more general than, can this classical equilibrium macrostate transform into that one spontaneously? The price we have to pay is we have to do more math to answer our question. We need to check that more than just one inequality hold. But what are resource theories? Or first, how about just resources? I think of a resource as something that is scarce and valuable because it might be useful for performing some operational task. For example, money is a resource. We can use it to buy lab equipment if we're experimentalists, or coffee if we are theorists or philosophers. And money is scarce. As it is said, money does not grow on trees. Now, what are resource theories? These are simple models developed in quantum information theory for situations in which the operations we can perform and the systems we can access are constrained. For example, in thermodynamics, we'll often think about an agent who is in a fixed temperature environment and so can access easily only systems at thermal equilibrium relative to that temperature. And in thermodynamics, the first law of thermodynamics constrains all operations. Energy must be conserved. In this simple model, we will say that some operations and systems are easily performable or accessible, and we will approximate them as being completely free, costing nothing whatsoever. And an agent can access and perform as many of these as desired. Everything else is scarce. It might be useful for, say, sending information, quantum information down a channel or charging a battery. And so we call these other things resources. Using a resource theory, we ask which transformations can happen for free, which transformations cannot happen for free, and in general, what is possible and what is impossible. So here's the model of a thermodynamic resource theory. I'll actually present a simplified version of the model. Generalizations are possible, but they are not quite as easy to explain. When using a resource theory, we'll be thinking about how some system of interest transforms. Let's call it S. It's at least one discrete degree of freedom. A favorite example is a set of two energy levels, a qubit. And a simple example of that is the spin degree of freedom of an electron that is, say, in a magnetic field. Something that is not an example of what I'm talking about is the position degree of freedom of a particle in a continuous space. Continuous spaces are much more difficult to deal with mathematically. They involve things like rigged Hilbert spaces. And besides, experimentalists have great control over discrete quantum systems. So why not use them? Although the results I'm going to talk about may be extended to continuous systems. Our system will be in some quantum state rho. By quantum state, I don't mean a wave function. So a wave function is a representation of a quantum state in a very special class, pure states. It's the state of a quantum system that's not entangled with anything else. In general, a quantum state is the state of a quantum system that might be entangled with something else, might not be entangled with something else. The notion is quite general. Technically, I mean, when I write down something like this rho, a trace one positive semi-definite linear operator, but those details don't really matter very much for the sake of what we're going to talk about. Our system of interest in our simple resource theory model is in an environment that's at thermal equilibrium with respect to some fixed temperature T. Here is the model for every free operation. Every free operation consists of up to 3 steps. Some piece of the environment, let's call it E, that is in a thermal state, can come over and contact the system of interest. S and E can couple together in any way that conserves their total energy or obeys the first law of thermodynamics. Then this E can drift away from S again. From that model and quantum theory, we can derive what are kind of sometimes called second laws. These second laws answer 2 questions. First, suppose that I have a state rho and I have in mind a state sigma. Can rho transform into sigma for free? Or can rho not transform into sigma for free? These questions are quite general. Neither rho nor sigma needs to be in equilibrium states. Our system of interest S can be quantum or quasi-classical, by which I mean not having coherences, not entangling with anything, but at least having these discrete energy levels. And our system of interest can be small or large. It doesn't have to be in the thermodynamic limits. The price for this great amount of generality is, in order to answer our questions, we can't check just one inequality, like the conventional second law. We have to check a whole family of inequalities. We have to do more mathematical legwork. In fact, there are 2 families. One subfamily governs probabilities. Suppose that we have a system in a state rho. Suppose we measure the system's energy. We'll get one of probably multiple possible outcomes, which obtain with certain probabilities. An analogous statement is true of sigma. And so how one set of probabilities transforms into the other set of probabilities is governed by one subfamily of inequalities. The other subfamily governs coherences, wave-like properties, or more technically, if we represent rho as a matrix relative to the energy eigenbasis, the off-diagonal elements are the coherences, so just the wave-like properties of the state. The math behind this result is rather fun, at least I think so. It's called majorization. It falls within the domain of probability theory. It was actually developed by economists in the early 20th century because they needed a toolkit for quantifying how unevenly wealth was distributed across a population. So majorization theory features things called Robin Hood transfers, which model the stealing of money from the rich and the giving of money to the poor. And Robin Hood transfers actually have relevance in thermodynamic resource theories. They're related to the process of thermalization. You can find details about that in this paper. These are the early and landmark papers that concern the second laws, as they are sometimes called, derived from thermodynamic resource theories. And prosier explanation of these results, as well as of Robin Hood transfers, appears in chapter 11 of this book. We've talked about one extension of the second law derived within quantum thermodynamics. Now I'll talk about a different kind of extension. We can use correlations, including entanglements, to push heat from a colder system to a hotter system, even on average. Entanglement, as you probably know, is a relationship that quantum particles can share and classical particles cannot. It allows for very strong correlations between measurement outcomes and was the subject of the Nobel Prize in Physics 2 years ago. The results that I'm going to talk about come from this paper that I think is a very cute paper by David Jennings and Terry Rudolph. Now we're going to talk about a different formulation of the second law, one put forth by Rudolf Clausius. Clausius says heat can never pass from a colder body to a warmer body without some other change connected therewith occurring at the same time. We would add the phrase on average to this statement because, again, we know that bodies consist of small particles that move around randomly. Sometimes they move oppositely the way we would expect. So for instance, if you go into your kitchen, you open the refrigerator and just let the refrigerator sit, mostly heat will flow into the refrigerator. A little bit of heat will flow outward, but mostly heat will flow inward. Therefore, if we want to keep the refrigerator cold, then we need to plug the refrigerator into an outlet and spend work or energy that is reliably extractable and coordinated and harnessed in some sense. This expenditure of a work resource is the some other change being referred to in this Clausius formulation. More abstractly, we can think about a system at a higher temperature, TH, and a system at a lower temperature, TC. If we let the two exchange heat, mostly heat will flow from hot to cold, although a little bit will flow in the opposite direction too. And we monitor how much heat has flowed from hot to cold, and we see that the cold system is heating up. Is these such observations that give us the impression that time is passing. This phrase, some other change, in the context of the refrigerator, was realized with the expenditure of work. There are some other changes that can be realized that we might find a little more surprising. And to find our way to those some other changes, let's do something that appears to be going onto a detour, and let's ask the question, what does it even mean for a classical system to have a temperature? Well, suppose that we measure the system's energy. If the system is usefully described by statistical mechanics, the outcome is a random variable. Suppose that our probability of obtaining the outcome E is proportional to an exponential, the negative sign, the energy in the numerator, Boltzmann's constant, and some real number over here. If this is the case, then we will call the real number the temperature. Now, what does it mean for a quantum system to have a temperature? The system needs to satisfy the same condition as the classical system, plus an extra condition on coherences. Technically, the coherences of the state relative to the energy eigenbasis must all vanish. So suppose that we have a hot system and a cold system. Suppose that we measure each system's energy. We'll obtain two random variables, EH and EC. Two random variables in general, and as exemplified by EH and EC, can be correlated. We can, in a very simple example, see why or how. Suppose we have, to start with, two independent random variables for contrast. Suppose that we have two independent coins. We flip the coins, and which face lands upward is our random variable. We'll call the first random variable C1. It has the possible values heads and tails, and the second random variable is C2. Suppose that our coins are fair coins. If we flip coin C1, our probability of seeing heads land upward will be 1/2. The probability that tails lands upward will be 1/2 as well. And we can make analogous statements about random variable C2. We can also look at joint events. What's the probability that both coins will land heads up? Well, since our variables are independent, that joint probability equals the product of the two individual coins' probabilities, namely 1/2 times 1/2 or 1/4. We can go through reasoning of the same sort for every pair of possible joint outcomes: heads, 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 tails, tails, heads, and tails, tails. In every case, the joint probability is 1/4. Now, suppose that our random variables are correlated. I don't really know of a good way to represent something like coins that are correlated, so I'll just put tildes on my coins and my variables. So the new variables are tilde C1 and tilde C2. As before, each variable can evaluate two heads or tails. If we can arrange things such that if we look at each coin individually, it appears to be a fair coin with probabilities of 1/2. However, perhaps the joint probability of heads and heads will be 1/2. Also, suppose that the probability of tails and tails is 1/2. So that the probabilities of the mixed outcomes, heads, tails, and tails, heads, are both 0. In other words, if we know the outcome of one coin flip, we automatically know the outcome of the other coin flip. If we have one heads, we'll get another heads. If we have one tails, we'll get another tails. So if we have just information about one coin, one random variable, then thanks to correlations, we implicitly hold an information resource about the other random variable. In other words, we can think about correlations as an informational resource. Now, let's return to thinking about quantum states from thinking about random variables. We will often quantify information in the context of quantum theory with the von Neumann entropy. The von Neumann entropy of a state rho is the negative of the trace of the state times the log of the state. And this entropy can be interpreted pretty straightforwardly as our average uncertainty about the outcome of a measurement of the states. Now, I am, again, talking about information in the context of thermodynamics. I don't want to make any claim like anytime we have an informational entropy, it can be interpreted as a thermodynamic entropy. We need to be really careful. So actually, when I saw the von Neumann entropy pop up in this Jennings and Rudolph paper, I was very skeptical. Jennings and Rudolph said, the identification of the information theoretic quantity with a thermodynamic variable has generated a long history of debate. However, we do not add to this debate here since the operational and mathematical correctness of our analysis holds independent of such interpretation issues. And I was surprised to find by the end of the paper that I agreed with them. Their derivation is very straightforward. It involves some algebra and basically the definition of expectation values. Another entropic quantity that we can use to quantify information contents is the mutual information. The mutual information between a hot state and a cold state is the von Neumann entropy of the hot state plus the entropy of the cold state minus the entropy of the joint state. This mutual information's significance is it's the amount of information that's shared between the systems, or the information one system has about the other. The Bible of Quantum Information and Computation, Nielsen and Chuang's textbook, has this suggestive image to give some intuition about what mutual information signifies. Suppose that we know the form of rho hot. Still, we're somewhat ignorant about the state. About the system. Suppose we measure the system. In most cases, the outcome will be random. We won't be able to predict the outcome with certainty. We can just talk about the possible outcomes and their probabilities. So we still have some uncertainty. And that uncertainty is represented or quantified by S of rho hot. We can tell a similar story about S of rho cold, our uncertainty about the cold system. So imagine taking this uncertainty and adding it on to this uncertainty, and then subtracting off the uncertainty about the system as a whole. So imagine performing a measurement of the joint state. What do we have left? This purple shared area. How come? Because we added it on once in this term. We added it on another time in this term. And then we subtracted it off only once in the final term. So we have one copy left. And this shaded purple shared area is the mutual information between rho hot and rho cold, the shared information. So let's use these tools and see what we can say, or what Jennings and Rudolph derived, and we can easily rederive thermodynamically. So two random variables or quantum states can share correlations, and so encode an informational resource. We can use that informational resource as that of some other change. The expenditure of that resource is that some other change that can put push heat from a colder system to a hotter system, even on average. Here's a setup, partially as a reminder. We have a hotter system and a colder system. The two might begin with correlations, even though each one, if you look at it individually, looks like just an ordinary thermal system with some temperature. We assume that the two of them will interact with each other, so they have the opportunity to exchange heat, and no energy is coming in from the outside. No work is being performed on the system. These two systems aren't interacting with some external heat bath. QH will denote the average amount of heat that flows into the hotter system. And this, when I say average, I mean an average over trials in the sense of an expectation value. So this is the generalized second law that Jennings and Rudolph derived. It states that the average heat flowing into the hotter system times factor 1 over the high temperature minus 1 over the low temperature is at least the change in the mutual information during the interaction. We can start to get a handle on this generalized second law by looking at a simple case. We can recover a more conventional statement of the second law. The second law conventionally is applied when the systems start out uncorrelated. We just have a hot system over here, a cold system over there, and they have never spoken to each other. If the systems are uncorrelated initially, then their initial mutual information vanishes. So all the mutual information can do over the course of the interaction is increase or remain constant. Therefore, the right-hand side of this inequality is at least 0. Now let's look at this factor. TH is a high temperature, so this number is large, so this fraction is small. So this factor is negative. Where does that leave us? Now this side is positive. This factor could be negative, so this factor has to be negative or 0. And if QH is negative, and we said that QH is the average amount of heat flowing into the hot system, then, on average, positive heat must flow out of the hot system. And indeed, such behavior is consistent with the second law of thermodynamics as we ordinarily know it. However, the systems can begin with correlations. And so our earlier conclusion can be flipped. So the mutual information can go down during the interaction, or the correlations can be used up. So if this side of the inequality is negative, then even when this factor is negative, this factor can be positive. So a net positive amount of heat can flow into this hotter system even on average. Entanglement, we said, allows for correlations that are stronger than any we can achieve with just classical systems. So you might expect that if the initial state is entangled, we could observe a particularly large amount of heat flowing into the hot system on average. Indeed, suppose that we monitor the heat flowing into the system on average. If that amount of heat lies above a certain threshold, we can conclude, using Jennings and Rudolph's paper, that the initial state must have been entangled, if quantum theory describes our world accurately. In this sense, we can use anomalous heat flow as a thermodynamic witness for entanglement. I think that this result is cool because usually we use information theoretic tools in order to identify entanglement or use quantum theory to shed new light on thermodynamics. But now we can monitor a thermodynamic phenomenon in order to observe or have a signature of a quantum foundational or quantum information theoretic phenomenon, namely entanglement. Okay, now we have covered 2 extensions of the second law that come to us from quantum thermodynamics. The third extension I'm going to talk about actually arose within non-equilibrium statistical mechanics, but They were then appropriated by quantum thermodynamics. So I'm going to talk for simplicity in large part about classical systems here, but quantum versions of these fluctuation relations have been derived too. Here are some key properties of fluctuation relations. They are equalities. They are equalities even when describing systems far from equilibrium. The ordinary second law of thermodynamics is an inequality. That is, entropy, or the final entropy must be greater than or equal to the initial entropy. That non-strict inequality is an equality if the process is an equilibrium process. If the process is quasi-static, happens so slowly that the system, if the system is already in equilibrium so that its entropy doesn't change. Equilibrium is a very, very restrictive situation. It takes a very, very special system, at least in our everyday experience of the world, to be in equilibrium. The systems that we interact with, we ourselves, are in large part far from equilibrium. So these equalities in governing far from equilibrium systems are particularly powerful. An inequality doesn't tell us the exact value of the final entropy. An equality is a relatively strong statement. As I mentioned, fluctuation relations were first proved for classical systems, then they were proved for quantum systems. And from fluctuation relations, we can derive what is very often in the literature called the second law. And it is the second law if you will take the first law for granted. It's actually an implication of the first and second laws. But it's often called the second law. I'll provide more details about that. And fluctuation relations give us detailed predictions about single trials. Let me provide more information about all of these key properties so that they don't feel so abstract by presenting one illustrative use of a fluctuation theorem or a situation in which we can derive a fluctuation theorem. So consider a DNA hairpin. This is a single strand of DNA that has a loop at the top and these two arms extending outward. This hairpin is classical if it is floating at thermal equilibrium at room temperature in some aqueous solution that has some temperature T. Suppose that we measure the hairpin's energy. The probability of obtaining some outcome E will be this Boltzmann factor. The partition function is defined as the normalization factor. So an integral over the energies of the density of states times the Boltzmann factor. Since this DNA hairpin is at thermal equilibrium, it has a free energy. The relevant free energy, since the hairpin is exchanging just heat with its surroundings, is the Helmholtz free energy. The Helmholtz free energy often quantifies how much work a system can perform. It equals the negative of Boltzmann's constant times the surroundings temperature times the log of the partition function. I'll call this free energy F sub I. Let's define the forward process as follows. We can use a laser beam to trap one end of our DNA hairpin. This laser beam will be used to form optical tweezers, which led to the awarding of a different Nobel Prize. We trap this end of the hairpin. We stick a microscopic bead on this end, as well as this end, so about the size of a bacterium. We use a micropipette to grab onto this bead and pull it to the side. We will pull the bead or stretch the strand through some predetermined distance. We can do this at whatever speed we please. We just pick some speed beforehand. For stretching the strands, we have to perform work. How much work do we have to perform? The amount is a random variable. It'll vary from trial to trial. For example, in one trial, a water molecule can kick the DNA strand in this direction over here. In another trial, a water molecule can kick the DNA strand in this direction over here. But suppose that we perform many, many trials. Each time we measure the amount of work required. From the outcomes, we can infer the probability that the next trial of our forward process will require an amount W of work. After we have stretched the strands, when the strand is sitting here taut, if we let it sit around forever, staying taut, the strand would rethermalize to the temperature T, just with a different Hamiltonian than beforehand. And after the strand rethermalized, it would have another Helmholtz free energy. Let's call it F sub F. It depends on the final in this imaginary epilogue, final partition function. Let's define as delta F the difference between the final free energy and the initial free energy. If we combine the first and second laws, we can conclude that in this process, the average amount of work that we will have to perform to stretch the strand is at least delta F. Delta F is the amount of work that we would have to perform if we stretched the strand quasi-statically, so slowly that the strand always remained in equilibrium. And so this is what sometimes people call the second law, or it's the second law if you take the first law for granted. And it is an equality just if the process is an equilibrium one. We can also define a reverse process. Imagine that we begin with the stretched strand and imagine that this strand begins at thermal equilibrium in its stretched position. We can allow the strand to collapse so that we recoup work. How much work will we be able to recoup? Again, that is a random variable, but denoted by P reverse of negative W, the probability, or really the probability density, that in the next trial of the reverse process, the amount of work that we will recoup is W. From these objects that I've introduced, these forward and reverse processes and these probability distributions, we, together with the laws of statistical mechanics, we can derive Crookes' theorem, developed by Gavin Crookes. He's not a criminal. The placement of the apostrophe is very important. As a matter of fact, one of my most prized intellectual possessions is an email from Gavin Crookes. In my first year of grad school, I wrote my first paper about Crookes' theorem and received this email afterward from Gavin. It said, "That's the most interesting paper you have on the archive. May I particularly commend you for putting the apostrophes in the right places." So punctuation does matter. Here is Crookes' theorem. It contains the ratio of the forward probability to the reverse probability. This left-hand side depends on some amount of work, a random variable. It appears in this exponential on the right-hand side. Here's the difference between the actual amount of work required and the amount that would be required if the process were quasi-static. And as usual, we have one of our favorite thermodynamic energy factors. This equality implies we are, and by the way, Crookes' theorem is a prime example of a fluctuation relation. We are exponentially more likely to lose an amount W of work than to gain it. Suppose that W is very large. This is the probability that we'll lose a large amount W of work on a forward trial. This is the probability that we'll gain a large amount of work W in a reverse trial. If W is large, this exponential of W is really, really large. So this probability of losing a large amount of work is huge compared to the probability of recouping that amount of work. So the fluctuation theorem clearly encodes the spirit of the second law, that is, you can't win. Via just 3 mathematical steps, you can infer the statement that we looked at earlier, which is, again, sometimes called the second law. So from the fluctuation theorem, we can recover the second law conditioned on the first law. But this fluctuation relation also gives us pretty detailed information in terms of probabilities about what happens in every single trial. Furthermore, with a little bit of math, we can upper bound our probability of being able to get away with less work than expected in any given forward trial. And if I recall correctly, as you might expect, that probability is exponentially small. So we are unlikely to get away with spending less work than expected. And Crookes' theorem was first put forth in this paper. It was preceded by Jarzynski's equality, which is another very famous fluctuation theorem. Both these fluctuation theorems are discussed together with experimental tests in chapter 9 of this book. I talked about one way in which we can kind of bend around the second law. We could spend entanglement to push heat on average from a colder system to a hotter system. And in the context of fluctuation theorems, we can sometimes get away with spending less work than expected, but with a low probability. That's also a kind of bending around the second law. There are other ways we can bend around the second law. At least one is discussed in chapter 7 of this book. Namely, we can imagine running an engine between reservoirs that are in squeeze states. So a heat engine, a conventional heat engine, has access to a hot reservoir and a cold reservoir. Heat flows from the hot to the cold, and from the heat flow, the engine extracts work. Carnot's theorem is an upper bound on the efficiency of the engine and is equivalent to the second law of thermodynamics. Also, this year is the 200th anniversary of Carnot's theorem, so I hope you are all planning to celebrate. If we have a quantum engine that can access quantum systems, then we can make one of those systems, according to certain ways of probing it, look like it's a thermal system with some ordinary temperature, but in fact have squeezing. So a system is squeezed if it has an observable that has a really, 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 really low uncertainty, such that its complementary observable has a very, very high uncertainty. And squeezing is a quantum phenomenon, since I'm talking about quantum uncertainty as in uncertainty relations along the lines of Heisenberg's. And this squeezing has been argued to serve as a quantum resource that can allow the engine to appear to violate Carnot's theorem. But in fact, Carnot's theorem was not intended to be applied to quantum systems that have access to squeeze states. So this is another way we could say that we bend around the second law. So in conclusion, we saw that using quantum thermodynamics and non-equilibrium statistical mechanics, we can generalize the second law and derive more refined versions of the second law. We saw 3 examples. We can derive second laws of thermodynamics from resource theories, simple models put together in quantum information theory. We can use correlations to push heat from a colder system to a hotter system, even on average. We can push a particularly large amount of heat if we have entanglement. We also saw fluctuation relations, which are equalities, even far from equilibrium, and that imply a second law-like statement, but give us more detailed information. But in my view, the spirit of the second law appears to survive from the 1800s, although the wording of the second law has needed updating. I don't know of a way to use quantum resources to break the second law, but we at least can use quantum resources as new sorts of resources to bend around the second law. This conclusion can help us understand quantum foundations better using thermodynamics. We not only need to update thermodynamics thanks to quantum theory and using quantum information theory, but we can also move in the opposite direction. Thanks for your time.
All right, so we're about to start the discussion Q&A. The first hand I see is from Wayne. Wayne, please go ahead.
Okay, thank you. Thank you, Nicole. That was a really clear talk. I guess I have a question about the Jennings and Rudolph thing. I want to know if I'm understanding it correctly. So you can move heat from a colder to a hotter thing, but the reason it doesn't really violate, say, the cardinal bound of efficiency is, or the closest statement is, there's some other change that's happening, right? And what you're doing is you're decreasing the correlation between the two systems and using up that resource. Is that right?
Right.
Okay.
So this falls into the category of the some other change. It's just maybe a
Right.
surprising kind of a change.
Yeah, not the sort of thing Clausius would have thought of, but counts as some other change. Okay, so this is good because like in space of a few minutes, I went to regarding this as counterintuitive to sort of like exactly what you should expect. Because tell me if I'm thinking about it right. So if I have two systems and I want to minimize the free energy subject to the constraint that I have this expectation value of energy for this one and this expectation value of energy for that one, like where one is higher than the lower. Then that would be canonical state uncorrelated for the two at those two different temperatures. And if it's correlated, then it doesn't minimize the free energy. So if I bring it down to an uncorrelated state, then I can get some work out. Is that the idea?
Mhm.
Yeah. Okay.
Yeah, they didn't actually have, yeah, so they were
Good.
calculating just the free energies of the individual systems. But yes, at the very least, the spirit of that is completely correct. And they did do a free energy minimization problem.
Okay. All right. Cool.
Okay, great. Thanks, Wayne. Joanna, you're next.
Thank you. I have a clarificatory question. Could you explain in more detail that distinction which you use between breaking a law and bending around a law?
I would say that a law is broken if we make an observation that is inconsistent with the law. And I would say that we're bending around a law if, when we first look at a problem and first hear about it, have the impression that the problem breaks the law. But in fact, when we look more closely, we can see there's actually a good reason that explains why the law isn't violated. At first glance, the setup appears to be consistent with the assumptions behind the law, but in a subtle way, the setup doesn't actually satisfy those assumptions.
Thank you.
Thanks, Joanna. John, you're next.
Great, thanks. Thanks very much, Nicole. It's great talk. You mentioned, I think, if I understood correctly, you mentioned at one point that the statement about being in equilibrium had to do with the off-diagonal elements of the density operator and the energy basis vanishing, which is natural enough from a physics background. But how does that enter the discussion when one's sort of embedding this in kind of an information way of thinking about things?
So we were talking about thermal equilibrium. We said when a quantum system is in thermal equilibrium, it's in a state whose coherences relative to the energy eigenbasis vanish.
Right.
So another way of saying that is the state is diagonal with respect to the energy eigenbasis, which means that the state commutes with a Hamiltonian. And if the state commutes with a Hamiltonian, then under evolution by that Hamiltonian, the state remains constant,
Okay.
and hence the use of the term equilibrium.
Okay, and even if suppose there were some degenerate states and so on.
Then I would say that the Hamiltonian has technically infinitely many eigenbases, and there is an energy eigenbasis with respect to which the density operator is diagonal. And so if you kind of tweak my wording to say kind of like, there exists such that there is diagonality, then the state will still satisfy the definition.
And do people worry about in sort of the kind of modern framework you've been talking about, do people worry about how a system gets into such a state? Is that well understood or not understood at all? Or I'm sorry, I'm a bit of a novitiate with all this stuff.
It's of great interest to a very wide community. And there's a lot of work on how long it takes, so bounding the time required for thermalization. Also, some systems resist thermalization for abnormally long times for different reasons. So sometimes there's a difference between a wide difference between energy scales in the Hamiltonian that can lead to pre-thermalization of the system. It comes to some state that's kind of metastable. The system will be here for a while before eventually heading off to thermal equilibrium. And which systems thermalize, why, how, and how you can avoid thermalization are all very much of interest.
Okay, thanks very much.
Thanks, John. We don't have any other hands up right now, but I always have questions. So whenever we run out of questions in the list, I have some questions. Oh, wait, we have questions from Gabriella. All right, so I'll save mine until after Gabriella. Go ahead, Gabriella.
So first of all, thank you for the talk. I really appreciated the part, the third part, with the clarification between the sort of the version of the law of the second law of thermodynamics and the fluctuation, because that's something that I was never, like, I never heard in such a clear way. So thank you for that.
I'm glad.
The question is, when you do have heat transfer from cold to hot because of mutual information, the entropy of the overall system, what does it do? It stays the same, increases, and certainly it's not going to decrease, I assume.
Yeah, probably increases monotonically.
Okay.
Yeah, I don't recall seeing that as part of the derivation, but it feels like a sanity check that you can do for a homework problem. I mean, so one kind of simple example way of thinking about it is, suppose we take the limit in which the difference between the two systems' energies becomes really, really small. Then you can cause the the two systems can just be maximally entangled with each other. And then the whole thing is in a pure state. And that has an entropy of 0. And if you do anything to decrease the correlations, so make the state not pure, then automatically you're increasing the total entropy.
Okay, so that's what I expect. So the increase of the entropy is still applied sort of to the whole system instead of the parts.
Thanks, Gabriella. So I have a couple of questions. At several key moments during the discussion, Nicole, I think you or the papers or in your work, you invoke Hamiltonians. I guess in a thermodynamic context, I'm always curious then how robust some of these results are when one generalizes from closed systems with a well-defined Hamiltonian to open quantum systems that might not have a, that might not be evolving even approximately unitarily with some well-defined Hamiltonian, like systems evolving according to some more general master equation. I guess I'm just curious to what degree these results can be applied to more general open quantum systems, and if you know.
Yeah, well, suppose we start with the resource theory. There we had a system of interest S that is interacting with its environment. So we can just always cast the system and environment composite as undergoing the unitary, but the system undergoes some other channel. And the Jennings and Rudolph paper is probably so cute and simple because it concerns quantum systems. On the other hand, closed systems, but on the other hand, the hot system and cold system are supposed to be in reduced thermal states. So that's at least kind of promising for the notion that we should be thinking about open systems is that a thermal system, at least, has been open in the past. And let's see. Oh, they wanted for their system not to interact with the rest of the universe because if we're performing work on the system, then that could be cheating. We could be using our work to pump heat in the wrong direction. In general, quantum thermodynamics incorporates master equations. And so that's just one of the favorite toolkits of quantum thermodynamics. Quantum thermodynamics consists of lots of subfields, and different subfields have their own favorite toolkits. So I didn't talk about results within a master equation subfield, but they exist. And I expect we could probably dig up some similar stories there. Now, open systems have been a particularly thorny problem for fluctuation theorems. Fluctuation theorems in the quantum regime bump into the problem of the distinction between quantum heat and work. If we have a quantum system that is interacting with a heat bath and also having work performed on it, how do we distinguish what is heat and what is work? We like to define physical quantities that we can measure, but if we measure the system's energy, then we probably disturb the energy because the system probably isn't in an energy eigenstate. And if we can't even ascribe to the system a well-defined energy at one point, what hope do we have of ascribing a particular type of change in the energy to the system? There are all sorts of solutions proposed to get around this. And some involve weak measurements, some involve separating the heat exchange and work exchange steps, or especially in the context of fluctuation theorems, lots of proposals.
So I have another couple of questions. This goes, I guess, a little bit beyond the scope of your talk, but I just thought I would ask. I'm particularly interested in the connection between thermodynamics and even just special relativity, right? Forget GR. What's going on right now with work in quantum thermodynamics and its intersection with relativistic systems, if anything?
I would go first to the relativistic quantum information community. People there like to think a lot about unruh radiation and various types of detectors and extracting work from being in an unruh setting. So they use tools like quantum mechanics and curved spacetime. So I know there is a lot of work there. I just haven't checked in recently a whole lot with the community. Though they've also had their intersection, for instance, with fluctuation theorems. I had Eduardo Martinez lecturing me about how projective measurements in quantum theory make no sense whatsoever. And so you need to find another formalism through which you can even define work in the context of quantum field theory. So some people working in this area are Eduardo, Yvette Fuentes, others in Waterloo and elsewhere.
Thank you. I guess my other question is, so at the end of your talk, you said something very interesting about how quantum mechanics can change how we think about thermodynamics, but in turn, quantum thermodynamics can shed some light maybe on quantum foundations. And I don't mean to put you on the spot at all, but if you have any thoughts about any larger thoughts about what quantum thermodynamics has to tell us about, small or large, new or old questions about quantum foundations, I'd be very interested to know what you're thinking.
I usually cast quantum thermodynamics as having three goals. One is the one that I talked about, most extending the laws of thermodynamics. Another is, we know from quantum information processing that quantum phenomena such as entanglement can enhance information processing tasks like securing information. Just as there are information processing tasks, there are thermodynamic tasks like charging batteries and performing work and extracting work. So we can similarly ask, how can we use quantum phenomena to enhance those tasks? And that's an operational way to understand better what quantum theory can accomplish and classical mechanics cannot. Also, and so I see as kind of a third goal of quantum thermodynamics is to look at a system that is storing and processing energy and other thermodynamic quantities and ask what behaviors does it exhibit that no classical system could exhibit. And I have been thinking a lot sort of in that direction over the past few years. I've been really fascinated by the notion that for decades throughout statistical mechanics and thermodynamics, when we have thought about a system exchanging heat with a heat bath and maybe particles and electric charge and so on with its environment, we've implicitly, in many cases, assumed that the things that are exchanged are represented by operators that commute with each other. But a system that is quantum can exchange the x component of its spin and the y components of its spin and the z component of its spin with an environment. And what happens to thermodynamics if these quantities that are exchanged thermodynamically don't commute with each other? And my group recently published a perspective on this small growing subfield. By now, people have found a number of thermodynamic phenomena that change if these exchanged quantities don't commute. The eigenstate thermalization hypothesis, one of our best toolkits for understanding why closed quantum many-body systems thermalize internally, that breaks down. The amount of entanglement across the system can change if things fail to commute with each other. Something kind of on the way to chaos, at least, can become more restricted. So I think of these results as heading in that third direction.
Very cool. Thank you very much. I don't see any other questions in the queue. If there are no additional questions, I think maybe we'll end a little bit early. So I want to thank Nicole again for leading a wonderful talk and a wonderful discussion and Q&A. Thanks so much.
Thanks for having me here.
It was a pleasure. And everybody else, I'm going to stop the recording now.